Hello, everyone. Welcome to the UFS Webinar Series. This webinar is hosted by OSTI, and this session has also been supported by WPO from OAR. The goal of this webinar series is to enhance communication and share advancement in all aspects of the UFS in both research and operational settings. My name is Bhavana, and I work with Yang Shui, who's the program manager at OSTI, to continue to coordinate and develop this webinar. Feel free to contact me if you have any comments and suggestions. Today's webinar is going to be presented by Dr. D from the Joint Center of Satellite Data Assimilation. He is going to be introduced by Tom Aliene, who's the director of JCSDA. Before we get started, I wanted to quickly go over a couple of housekeeping things. The first thing is I just wanted to walk you through where you will find the recording from the webinar and how to see an archive of all the webinars. So if you go to the UFS portal, which is at ufscommunity.org, and scroll down to the Stay Connected section, there is a button here to subscribe to new webinar announcements, and then you can view recordings of previous webinar over here by clicking on the UFS Webinar Archive. For today's today's presentation, the attendees' microphone and webcams have been disabled. You can raise your hand if you would like to be unmuted. We are planning to have the presentation last for about 45 minutes, followed by a 15-minute Q&A session. Please type your questions in the question box during the presentation. Tom Aliene, please go ahead. I'll hand it over to you to introduce Dr. Dick.
Thank you very much. Good afternoon, everybody. My name is Tom Aliene. I'm the director of the JCSDA, the Joint Center for Satellite Data Assimilation. It's my pleasure and honor to introduce Dr. Dick D today. Dick has a long experience with applied mathematics and data assimilation, and has had a very productive career in that field. He started with a PhD in applied mathematics at New York State University in the Current Institute of Mathematical Sciences, and has been occupying multiple functions, including a professor in Rio de Janeiro, Brazil, and in New York University, and has been a research scientist in Delft in the Netherlands. He's also been for a long time a scientist in NASA, what used to be called DAO, the Data Assimilation Office, and it's called now GMAO, and has contributed quite a lot in the field of data assimilation, including the adaptive Kalman filter, covariance estimation, modest bias correction, observation quality control. I had the pleasure to work with Dick in the European Center for Medium Wave Weather Forecasts, where he was working on the variational bias correction for the observations that's been implementing operations there. And he actually also worked for a long time at ECMWF on the Reanalysis project, ERA interim and then ERA CLIM, looking at coupled data assimilation, long time series of observations and homogeneous time series for climate studies that's being used around the world, and it's really spearheaded a whole field of science there. In 2014, Dick D became the deputy head of the Copernicus service for climate change at ECMWF, and he moved to the US in 2019, so about a year ago. Dick has joined us at the Joint Center for Satellite Data Assimilation, and he's the senior lead for observations, where his job is leading a team with multifaceted, ambitious goals, some of which are to develop a state-of-the-art suite of observation capabilities in that app store that we call the Unified Forward Operator. And another one is to have a very adaptive capability to estimate the observation impact. All right, so I hope I gave a fairly good overview of the extensive experience in data simulation, and without further ado, I'm happy to leave the floor now to Dick for hopefully a great presentation. Thank you very much.
Okay, can you hear me, everybody, or just one of you? Just
yes.
to verify. Okay, great. Thanks, Tom. That was much too long. Next time, please take less time so you can be much shorter. It just make me feel really old with all these things I've done in the past. But anyway, I was asked to talk about climate reanalysis and a little bit about best practices. And I think that means that I should talk about my recent experience at ECMWF, because that's where I used to be in charge of reanalysis, and we went through quite a long evolution in reanalysis, and we learned a lot of lessons, or are still learning a lot of lessons. So I think that hopefully will be useful to talk about. So 99% of this presentation is about ECMWF. I will say something about the Joint Center in the end as well, hopefully. But that's the story, and there's so many people to thank that I worked with and who are responsible for much of the work here. There's a whole big new reanalysis team at ECMWF led by Hans Hersbach, and then there's some very important people in my career at ECMWF or retired from ECMWF that I want to acknowledge. Saki Upala, who was in charge of the ERA 40 project, and Adrian Simmons, who was there from the very beginning and is still very productive, and Jean-Noël Thibault, who was my boss at the Copernicus service. So these are very important people that I worked very closely with, and I'm really grateful to them. So if we can go to the next slide, that just gives a very brief sketch of the story. It shows on the left.
Bhavana, can you click the presentation mode on the bottom right? Yes.
Yeah, thank you. That's good.
Oh, this doesn't work.
You see? Well, you have
Okay.
to swap screens, I think. Okay. So I'm not seeing the right thing now. Yeah. Is the display correct? No.
No.
Oh,
Yeah, I can't swap screens. I don't know why. So let's just stick to this in the interest of.
Yeah, except that you will not see some of the slides correctly in this way because there are some animations. So if you click on if you go back to what you did before, you should be able to swap displays on the top display settings. Yes, swap.
Okay.
That should do it. Okay.
Okay.
Great. So here's the story. It starts at the bottom left with ECMWF. I'll talk a little bit about the history of reanalysis at ECMWF. It was very much a research activity to support the development of the integrated forecast system, so their NWP system. But that evolved into a research activity that got bigger because it got support in the European Commission or the European Union to develop a new set of services in Europe about environment and change. And that led to several large collaborative research projects that allowed us to do some interesting development in data rescue, in coupled data simulation, etc. And ultimately that became the Copernicus Program, which is an Earth observation program with several operational services that rely very heavily on reanalysis. So that's basically the story, and it's a very happy ending story, or at least the current state, because where we are now is very different from where it started. We now have reanalysis firmly embedded in the operational services that ECMWF and other institutions in Europe provide. So that means that there really is sustained funding for development of reanalysis, observation, improvements, many other things, data services, and so on. So that's a really good situation to be in. Next, please. Next slide. Yeah, and that gives the next couple of clicks will give a quick history of reanalysis productions over the years at ECMWF. There are the atmospheric ones, which most of you know. We like to think that FIGI was the first real modern reanalysis, even if it was only a year long data set, but it was really the first digital global data set that described the complete circulation of the atmosphere. So in that sense, and based on observations, of course. So in that sense, it really was the first reanalysis, and it was a very international collaboration, and that set the tone for all the other reanalyses that followed. So it also explains why the latest reanalysis at ECMWF is called Era 5. We just decided to start counting forward instead of trying to make up new names each time. So this is atmosphere and land, and after Era 40 also included ocean waves, and beginning with Era 5 was funded or completely supported by the Copernicus Program. If you click again, please. There are also ocean reanalyses, of course, produced at ECMWF, and since recently also they include sea ice. Next, please. And then in the so-called Era CLIM projects that Tom mentioned, we were able to start developing century-long reanalyses, and the important outcome of this, well, there are several things that came out, but one of the more interesting ones is that we, for the first time, applied a coupled data simulation, and I'll try to show a little bit about that later on. Next, please. So then there, of course, are land products as well, and they're connected to the atmospheric reanalyses, and currently there is a product that is derived from Era 5, which is, again, supported by Copernicus. And next, please. And then there are the atmosphere composition reanalyses, also now supported by Copernicus. So that's really quite a lot of activity, and I want to show you or tell you why this is so important at ECMWF, that they have kept this going even before this kind of funding that we have today was available. Next, please. So here's just a list of reasons why it's important and really embedded in sort of the culture at ECMWF to do reanalysis. It's obviously a very good test bed for data simulation, because you really encounter all the different problems in a very useful way that helps you learn things about the forecast model, how to make better use of observations. That was really the original reason that people back in the early 80s, at the beginning of ECMWF, started talking about reanalysis, and that it should be done to help improve data simulation, basically. Lots of problems come up when you try to produce a reanalysis that actually fix bugs in the basic system. Then, of course, the data themselves are really useful for research and development. It gives you sort of a comprehensive verification data set for new developments in physics or whatever that you are doing in the model. It's also, and this is a really important one, it allows a whole new set of forecast products that are essentially probabilistic and require really good climatologies to be actually skillful. That's important. And then, as you know, because that's sort of the main driver, at least at NOAA, it's also really essential to have a good reanalysis if you want to do monthly and seasonal forecasting. And then the final thing is that they're also extremely popular with external users. And you know that probably everybody in the audience has probably used reanalysis data for research or whatever other purpose. And reanalysis data are also more and more used for other downstream systems in different, special areas, in different sectors of society and so on. And so they become more and more important for services development. And, this last part is what really is now delivering the sort of bread and butter that we need to keep going with reanalysis. So it's quite important for us. Can we see the next one, please? So I want to just give a very quick example of how reanalysis can be used in evaluating forecast performance. This is something really embedded at ECMWF in the culture to do this kind of thing. So we know that the forecast skill in NWP changes over time, hopefully in the positive direction, but due to several things. One is obviously the model and data simulation changes, higher resolution, better physics, etc., and the data simulation itself. The other is the changes in the observing system. And the third one is just the predictability regimes that change over time in the atmosphere. So when you look at a curve like the red one here, that's a skill score for precipitation in the high resolution NWP system. And you see that's improved over time, but not monotonically, and there are all kinds of variations. If you look at the same skill score from reforecasts from ERA interim, you see some of the same variations, but it's obviously more flat, and that's because it's using a frozen version of the IFS. In this case, it was a 2006 version, slightly lower resolution than the NWP system. So you see the curve starts pretty close to the red one, but then sort of stays in that same at that same level. Next, please. Now, if you look at the difference, then you essentially isolate the effect of the upgrades because the observing system is roughly the same, and the predictability, of course, is also the same. So that curve here is really useful because it does tell you actually what is the impact of model and data simulation upgrades. And so you can do this on a routine basis if you have a reanalysis that is updated in time, in real time. And it really helps, even in the short term, let's say of a few months, to assess impact of changes in the model. So next, please. And then, of course, you can do that for all parameters because reanalysis is very comprehensive. So you can see much more detail in this way. The only requirement is really that the reanalysis system should be at least similar to the NWP system. So, I mean, ideally, it should be the same system, but that's not practical because it takes a long time to produce a reanalysis. But it does mean that you have to redo a reanalysis occasionally. And with ERA interim, that was definitely the case. It was almost 10 years old, and it started to get old and too old. So, for example, it couldn't really handle lots of observations that the NWP system uses, and then the differences become too large to be able to do this usefully. Next, please. And then, as I mentioned, for probabilistic forecast products, which are becoming more and more popular and more important for, well, in Europe, especially for the member states, but everywhere, of course. And this is just an example of a very popular product, which is the Extreme Forecast Index that tells you, likely areas where certain types of extreme weather are likely to occur. And that's extremely useful for planning, of course. So this kind of product can only be produced if you have a good climatology, and really the value of the product depends on how good the climatology is. Next, please. So then I mentioned services. So now I'd like to actually spend 10 minutes or so talking about this whole Copernicus program and what it means. And it's something that has been talked about for a long time. So this is a slide from Adrian Simmons that was developed by people at this World Climate Conference, including Kevin Trenberth and others. And they were sketching out, how environmental services could be developed based on the capabilities that exist in weather forecasting, etc. And so the key thing about this plot is that right from the beginning, it was recognized that reanalysis, both global and regional, would be central in services like that because of the sort of comprehensive information that they provide, making the best possible use of observations and models in all time scales. So that was sort of the beginning of a central role for reanalysis in these emerging plans for services. Next, please. So that led to the Copernicus program, which is an Earth observation program in Europe. A large investment. The hardware is basically the Sentinels, which many of you know about. So that's the satellites that are operational satellites planned out for the next 20, 30 years to monitor atmosphere, ocean, and land and climate in many different ways. So that's, of course, a large investment. But the really unique thing about this program is that the initial investment from the beginning, it was recognized that without services, you really cannot benefit from any or from most of these data. So roughly 20% of the budget, which, let's see, over the last, the beginning of the period, the last 7-8 years, amounts to probably a little over 100 million euros per year was spent on development of services. And that's a lot of money. Can we go next, please? So Copernicus set off 6 different services, information services, 3 of them associated with the different components of the Earth system, land, marine, and atmosphere, and 3 cross-cutting services, a security service, emergency management service, so that's about fire warning, flood warnings, and so on, and the Copernicus climate change service. And the way that these work is they're supposed to use, of course, the Copernicus data, but any other data and models to be able to serve the users, the different use cases in society for environmental information. And the climate change service in particular was very new, something that didn't really exist at all and had to be built up from scratch. Some of the other ones had a legacy in other activities or research projects, for example, the Atmosphere Monitoring Service, which is about essentially constituents and air quality, had a history in the MAC projects and before that GEMS. So they had basically a 10-year startup in research, but climate change services really was a brand new thing in 2014. Next, please. So the way that works is that the European Commission selected different institutions to implement these services, and they chose ECMWF for 2 of them, namely atmosphere composition and climate. Next, please. So in particular, the climate change service, which is what I was part of over the past 7 or 8 years, is about providing climate information in a form that is useful for the different applications in society. So one of the most, let's say, difficult aspects of implementing this service was, how do you get from petabytes of data in difficult data sets with all of which have their own strengths and weaknesses, and how do you combine and process these data in a way that is suitable for users, or how do you allow users themselves to process these data? So the sort of infrastructure for the whole service is this so-called climate data store, and that provides access to all these data, including Reanalysis, but other space-based observation data sets, climate models for scenarios and projections, regional and global, and many other types of data. So that's a very interesting thing in itself. I'm not going to talk too much about it, but all the reanalysis data that you see now coming from ECMWF are coming through this climate data store. So there's a whole big service chain that makes it easier to access the reanalysis data and combine them with other data sets, including the tools that you need to do that. Next, please. So one of the things that is most visible, let's say, in the climate service is that I still say we, I'm used to that, sorry. We provided climate bulletins every month, which were produced very close to real time. You actually see them in the press nowadays because they come out so quickly, because it's produced using NWP methods, including reanalysis, to actually develop most of these data sets and change maps and so on automatically, and then they're supplied with some editorial content to make it useful for society. So there's a whole lot of activities surrounding that. Next, please. So that's about enough, I think, about the services. I just thought it was important to give you the context, because it is what really allows reanalysis to be sustainable nowadays in Europe. And that's, I think, very important to keep in mind, that the way that happened is that it was recognized that there are so many use cases that are extremely valuable, and that needs to be the focus. So that's a lesson, I think, that if we want to find a system for making reanalysis sustainable, we have to think about the users and what they really need. And the users include scientists, but probably it's more important sometimes to focus on users who are not research scientists, but who are working in applications and need to develop operational services where they can rely on proper access and support. So now the elephant in the room is, well, reanalysis and climate. I mean, I know that's a controversial subject that's been discussed over the years. Some people would say you really can't use reanalysis for climate. I don't agree with that, but you definitely have to be careful. So I do want to talk for 10 minutes about this question. Is it possible to accurately represent climate trends and variability in reanalysis? So the fundamental problem I think you all know about is that observation coverage changes over time, and models which are used in reanalysis have biases, and these biases are only partly corrected by observations. So that's already a big problem, because then it's very easy to see, and I like to use this little cartoon here, why you would get problems with representing trends, for example. So if you have, here's the black line represents the truth, let's say, the true climate, and you have observations in red, and you have a model that produces short forecasts in a data simulation system, but the forecast is biased, so it's always drawing up. And then what you see is that observations actually pull the forecast back to the truth, but only to, that that depends on the coverage. So if you are in a situation like this, you will actually see a false trend because the coverage changes suddenly and you have a smaller bias in the analysis than you had before. So this is very obvious and easy to understand. Next, please. The problem is that it's not only that, and it's not only the model biases, but the observations themselves are also biased in many cases, in most cases, I would say. And even the data assimilation methods that we have today may exacerbate the problem in many ways. So there are lots of examples. So I want to talk a little bit about this problem and some of the issues and pieces of evidence, but also mainly about progress. So next, please. So here's a real case that is exactly the same as that little cartoon that I just showed. These are 2 meter air surface, 2 meter air temperature anomalies. The difference between ERA 40, which is pretty old by now, and CRUTEM, which is one of the benchmark data sets based on station data. And these are type of data sets that NOAA also produces and NASA that are based on just climate reports from station data. And they're quite reliable, but of course they also have issues, but they go back very far. And this is what we usually refer to when we look at climate change since the pre-industrial period. So this difference here is obviously not flat. And it's known that ERA 40, the model in ERA 40 had a warm bias. And if you don't have enough SYNOP stations, in other words, to correct that, then you get exactly what we saw on the previous slide. So that's what you see here. So ERA 40 is actually okay after, or in the satellite period after 79. It's agrees pretty well with station data, but when you get less coverage, then it gets worse. Next, please. By the way, the spike in there in 1980 is a problem in the CRUTEM data set. So just to indicate, like I said before, observations also have problems. This happens to be a quality control problem where somebody swapped 1 month for another. And so that's how you got that spike. Next, please. That was corrected. So there's a new version of the observation data set, and now you see somewhat better agreement with ERA 40, but of course the bias problem remains. This is to illustrate what I said earlier, that observations have problems too, and they need to be worked on, and it takes time to find the problems and correct them. So that's just like reanalysis itself, these data sets also have to get constant attention, and there's work to do to improve them. Next, please. So if you look now at the atmosphere as a whole, so this is a nice set of plots from Adrian Simmons, one of his papers. He has several very good papers on climate variability and trends in reanalysis data. Very detailed, of course, just sort of his style. Lots of information in there. Really worth reading those papers if you have interest in this. So this gives a bit more complete picture for 3 different reanalyses, ERA interim, ERA 40, and JRA 55, Japanese reanalysis. And if you look, glance at the 2 plots, so they give the anomalies at different pressure levels in the atmosphere. You can see that the troposphere is pretty consistent among them. You see some clear signals like the 1998 El Nino, which has a very deep effect throughout the troposphere. You see on the right panel, you see the volcanic eruptions and the effect in the stratosphere. So all of that is in there, so that's good. But there are definitely differences, especially in ERA 40, which really had poor bias correction in many observation sources. And then in the stratosphere, you see things go pretty haywire in the ERA interim. There's this huge jump at 1 hectopascal, but it's also visible at 5. And really, you cannot really trust the trends over, 10 hectopascal and up. And we know how these things happened. I'll talk a little bit more about that later, but this just shows that there is definitely good information about trends. The lower stratosphere cooling is in era interim, for example, but you have to be very careful to use them. Next, please. Hydrological cycle is even more challenging. This is another plot that just shows for different reanalyses compared to observation data sets, so RSS and GPCP, which are at the bottom there. The different, this is for tropics, total column water vapor and ocean precipitation rates. Let's look at the bottom one, and you see that era interim is improved over the other reanalyses. It's still a bit high compared to the observation data sets, but there is discussion about whether the observation data sets are actually not too low. But the point is that variability is fairly well represented. Now, if we look a little bit more in detail, the next slide, please. Again, precipitation rates, but now just for era interim and era 5. And if you look at the left plot, notice that the scale here is much finer, so the differences are amplified so that we can see what's going on, but they are actually not that large. But the blue curve for era interim, you do see this dip in the early 90s, and then an upward shift again around 2005 and 2010. And we know that came from assimilation of SSMI data in the tropics using the first ever version in ECMWF of the rain-affected radiances assimilation. And it just wasn't good. There were some problems in it, and we know what that is. It was a risky thing to put it in a reanalysis. And it caused this shift. And you can see actually when you look at the different SSMI instruments flying, that it's actually proportional to the number of observations that were available. So this is another example of the observation coverage, but also complicated by wrong use of the data. And in era 5, there's a 10-year period between the models. So rain assimilation, radiance assimilation has really improved. So you don't see that anymore. That dip is still slightly visible, but it's almost gone. But now, if you then look at evaporation, you see we still have some problems there because they should be very close to each other, which they are from the mid-90s on to around 2012. But then things are going off again, so we don't really know exactly what's going on here, but there are definitely still lots of issues to improve on. Next, please. This is energy fluxes. It's really the same story. I see that I'm actually going very slowly, so I'm going to skip pretty quickly through this, but essentially the real problem here, if you look at the table and compare with the Trenberth et al. Estimates of the different energy flux components, which in that paper have been estimated from various sources, and it's sort of a benchmark to look at. You see that we still have in era 5 a large net budget at the surface, which is really wrong. That should be very close to zero, and it isn't. The problem is that the data simulation itself adds energy to the system, and with a model that is constrained by surface boundary conditions that are fixed, there's no way to take care of that. So the energy is absorbed by the surface, and that's wrong. So this is possibly an argument or a hope, let's say, that when we get to coupled models and coupled data simulation, there are perhaps ways to address this. Okay, more information in this paper that you've seen appeared several times from Hans Hersbach, which is the paper on era 5, which came out a few months ago. It's an excellent paper, and this is from that paper, and there's lots of discussion there if you're interested. The next, please. Okay, this is the last one on progress, and I like it because it's a very, it's a little bit subtle, but it's a good single picture that shows where we're heading, I think. So we are comparing tropical 100 hectopascal temperature, 12 months running mean. So this is lower stratosphere in the tropics, and 5 different reanalysis, different generations really. And what it really shows is the impact of RO data. And we all know that radio occultation data have been a great success in reanalysis because they act as an anchor. The biases are very small, and there are lots of them, and they're nicely distributed over the globe. So after about 2006, we have enough of these data in the reanalyses, with the exception of MERA, to anchor them. And you see that very clearly, that everything but MERA is pretty much at the same level at this point. So that's the impact of RO data. But what's interesting, I think, is when you look prior to the RO data, then you have the impact of model bias in the different reanalyses because they're not anchored. There are other observations, but there's nothing like the RO to constrain the 100 hectopascal levels. So you see the shift basically showing what the model biases are at that level. And you see that the 2 most recent reanalyses, MERA2 and ERA5, are very, very close together. So that's, I think, a really nice sign of progress, because what you want to see is that all of this eventually converges to the same thing or nearly the same. Okay, so next slide. I could show you much more of these types of examples of issues and progress and so on. But this is a list that I think covers more or less what it really takes to make progress in these things. It's work on input observations. So we need better input observations. There are lots of problems with them, especially the satellite-based. I'll show a few things in a minute. The model input itself, so the radiative forcing and boundary conditions, have to be improved continuously. Biases in the models obviously are sort of the ultimate culprit here, and they have to be addressed. But of course, that takes a very long time. It's very difficult. We have to improve the observation operators so that we model the older instruments better. We need to improve quality control of observations. The data simulation itself does not, in most cases, handle biases explicitly, with the exception of variational bias correction and weak constraint 4D VAR, but those are only really beginning to be used properly, and they're all, of course, more fundamental problems with attribution of biases in data simulation. But work has to be done on all of that. And then the one that you see at the end might not seem to belong there, but it turns out that many of these problems that we see in reanalysis are simply mistakes or things that weren't caught, because it's a huge production to run a reanalysis, and monitoring the performance in close to real time is difficult. It's much more difficult than LWP systems, because we're running often in parallel hundreds of days a week in a reanalysis, and you have to follow all of that very closely. So that is also a big issue. And I think that the message here is that there are so many different areas, and all of them, when you think about it, are not things that you can do in a few months or that you can do by yourself. So it's really indicating that progress requires distributed work, so collaborative work on many, many different fronts. That's really the only way to keep going and keep improving the quality of the reanalysis products. Next, please. So now there are a few slides that show a little bit more detail on some of these issues. I'll go quickly again because I think I'm going to run out of time. But this shows, for example, the variational bias corrections produced on sounder data, radiance data in ERA interim. And they're very interesting. You see for different channels, for different instruments, very strange behavior. Some of them are consistent with each other. Some of them are totally different. And there are many different causes for this. So if you click again, we've identified some of them. And this leads to work. Each of these things leads to work. There are lots of issues in all the bullets that I just showed you. The upper left one in the mid-upper stratosphere, that's an SSU issue. There's a pressure loss, CO2 loss because of a pressure leak in the instrument that made it drift. Other things later on in the stratosphere have to do with how the radiosonde data were used. There are fewer, more and more radiosonde data, but they weren't properly adjusted for biases themselves. There are Pinatubo effects, so that has to do with the model. So you see all kinds of issues here: models, observation operators, quality control, etc. And that leads to a lot of work by a lot of different people. So some of them are listed here, which then ultimately leads to improvement. Sometimes the data are reprocessed, sometimes the observation operators are improved, etc. Next, please. So a little bit quickly about ERA 5. New things in ERA 5 relative to ERA interim is basically the length. It started as a to reproduce the 1979 period to the present, but it has been extended back to 1950, and there are plans to go further back. There is better availability close to real time. At the moment, it's 2 to 5 days. That's really important for this services aspect, because there are lots of applications that want the updates immediately. The assimilation system, of course, is 10 years newer, so there are lots and lots of different benefits of that. The model input has been greatly improved. The input observations I'll talk about in a minute are really revisited almost comprehensively, and that I think is a major change over ERA interim, which was basically a very small scale project that happened to be very successful, but it just used the same things basically that were used for ERA 40. And I think that a really important thing about reanalysis today is that we have much better input observations that have been reprocessed and recalibrated by different groups, data providers, etc. So there are other improvements. Variational bias correction is applied to different, not just the radiances, but many other instruments as well. And of course, the resolution is much better than ERA interim. Next, please. So just a few slides. This is the input observations. You don't have to look at all of it, but the message here, there are actually 2 slides because it doesn't fit on one, is number one, there's a huge amount of instruments to be handled in a reanalysis like this. The blue ones, if you could you go back just a second to the previous? The blue bars indicate the observations that have been reprocessed, especially for ERA 5. So they were perhaps used in ERA interim, but they have been improved since then. And that's a major part of the observing system, including RO data, AMVs pretty comprehensively, ozone, etc. Next, please. So that's just a very complex picture, and a huge amount of work goes into this. And again, I should say that under Copernicus, there is funding for this for different groups. It's not just being done by ECMWF. In fact, most of it is not done at ECMWF. It's done by other groups in Europe and data providers and so on, satellite agencies. But it's all done for the purpose of improving reanalysis. I should say that since we're looking at these observations, that one of the things that the Joint Center wants to do is to develop an observation data store that can make it shareable. These type of data sets that have been especially improved for reanalysis could be shared on that data store. And we have ECMWF's word that they are interested in that, and that could really help the US effort as well. Okay, next please. This shows you analysis increments, a complete summary of analysis increments for ERA 5, globally averaged, and I think weekly or monthly average, probably monthly average. And there's a lot of information here. I don't have too much time to talk about what's wrong with it. There are definitely still some issues, especially in the stratosphere, which in some sense is even worse than ERA interim. But if you just flip, please, back and forth once or twice with the next slide, this is ERA interim. So you see much different amplitude. So the analysis increments in ERA 5 are overall much smaller. That's a very good sign. That means that the background is generally much closer to the observations. And there are fewer problems with jumps and sort of obvious artifacts. Ozone is a good example. In fact, the whole ozone input was pretty much new for ERA 5 with very good impact of that. Next, please. Spatial resolution and temporal resolution, you can see that in representation of storms. This is just a nice animation that shows the Florence event in 2018, and it makes a big difference to have hourly data on a much finer grid. Next, please. And this is also, I think, interesting. If you click once, you'll see here because we're now using ensembles also at the ECMWF. I know that that was not pioneered by us by no means, but now this is the standard for reanalysis, is to have some kind of ensemble to give some uncertainty information. And this 20th century reanalysis Sierra 20C, which is a coupled ocean atmosphere reanalysis, but using only surface observations. The ensemble there gives you an indication of the uncertainties, and you see if you look at so these are zonal means, obviously, and averaged over a whole season, and uncertainties are large where things are red and small where they're green, and you can see clearly that only in the northern hemisphere and in the tropics where the variability is less, you have smaller uncertainties, but basically southern hemisphere is not very accurate at all, and the upper levels aren't either. One click, please. But then if you look at ERA 5 in 1971, we are already in a much better position, because of course that means that we have lots of upper air data in the northern hemisphere that are used. So this is pre-satellite, but still there are plenty of other instruments to allow reducing the uncertainties. One more click. And then if you look at 1980, which is the beginning of the satellite era, you see that the southern hemisphere also becomes more well-defined. And finally, one more click. If you look at ERA 5 close to today, with the observing system that we have today, the spread in the ensemble indicates that we actually have pretty good accuracy in temperature for the whole season. Now, these are so-called synoptic uncertainties that the ensemble gives us. It doesn't tell us anything about error bars or trends and climate scales. That's something that we have to keep in mind. It's a whole different problem to estimate those types of uncertainties. Next, please. And we're gonna go skip this because I realize I'm running pretty late. So if you go one more. Just quickly, I wanted to add one more thing. Next thing that's coming up at ECMWF anyway is also in the US, as I understand it, is that the next reanalysis should be coupled with the ocean and sea ice. And this at ECMWF, we have some experience with this, because in the ERA CLIM projects, we developed a way to do that within the incremental 4D-VAR system that is in the IFS by essentially coupling the model in the outer loop and keeping the linearized analysis solvers separate, but only in the inner loops. So if you iterate that idea, so the outer loop is always using a fully coupled model, then the impact of observations in any of the components in the ocean or in the atmosphere are transferred through the coupled model to the other components. And the key thing here is that the final analysis is the output of the coupled model. And I think that's a really key feature that I would argue should be the case for almost any coupled data simulation system, because that's the only way that you can make sure that the analysis state is really consistent at the interfaces. If you click once, you'll see more detail, which I won't go into. So click twice, I mean once more, thank you. This is just an example of what can happen. So this was done in the ERCLIM project again, and we did both a century-long atmospheric reanalysis just for the atmosphere with monthly boundary conditions as usual for SST, that's ERA 20C. So that's the typical thing. You have monthly information about SST and you do essentially interpolation to get the daily boundary conditions, and that cannot be physical. The ERA 20C is coupled with the atmosphere, and in this case, the SST, external SST, was used as a weak constraint to relax to in order to control the bias, but the state was developed by the coupled model. So then you see, for example, these tropical instability waves appearing because they require the atmospheric, the ocean dynamics to be generated. And this is really a coupled phenomenon where the atmosphere responds to the wind stresses, but you need the coupling to really see these. And so this picture on the left, it may not be accurate. This is a Hofmuller diagram, by the way. It may not be fully accurate, but at least it's plausible. Whereas the picture on the right is not even plausible, and there's no way for it to be accurate. So that's, I think, an important thing to try to build into a design for a coupled data simulation system. And there are several papers by Patrick Laloriot on this, on the design of these reanalyses, the actual coupling in the data simulation, etc., that I recommend. Next, please. So, final slide. I've tried to explain that we are in a really happy situation in Europe, that there is this sustained funding framework given by Copernicus. The focus is on climate, which is actually good because that's sort of the fundamental thing in reanalysis that needs work. That also supports a lot of the work on improving the observational input. That includes, for example, satellite data rescue and reprocessing. So data rescue for satellite instruments is really important, and it's not often considered in our community so much, not as much as the conventional data rescue, but it's really key to try to make use of the early satellite instruments. And if we don't do it soon, then we won't be able to do it anymore. So the next global reanalysis will be coupled with ocean sea ice, I just explained. And finally, it's always been a collaborative effort. I hope that if you take away one thing from this talk, it's how much work is involved in getting the next reanalysis to be better than the previous one. And it involves work on all fronts. It's not just the model, it's not just the observations, it's also the technical parts and everything else. And it really requires collaboration. And I think now especially in my new role at the Joint Center, I really would like to help the effort that is happening here in the US, as I understand it, make it more collaborative and therefore better. The things that we can do or help with, at least, is to set it up so that the observation input can be shared, including the input that was used in ERA 5. So we have this vision on this R2D2 repository for research and data and diagnostics. Sorry, repository for research data and diagnostics, which will serve not only the NWP data simulation, but also reanalysis. We would like in our next AOP anyway to start addressing observation operators for older instruments so that they can support reanalysis production. And then we also are working really hard on making it very easy to evaluate observation impact in data simulation. And that should be possible to do also with the new ideas on coupled data simulation. We should be able to provide some tools to evaluate the benefit of each of these different methods. So I'm sorry I went a little bit too long. I blame Tom because he talked about the introduction was much too long. So it's his fault. But now I'm ready to answer one or two questions if you have any.
Dr. D, can you see the question box? If you cannot, then I can read out the questions to you.
Yeah.
Okay. So the first question is by, actually there's only one question, and it's by Shay Wei. He asks, Dr. D, could you please provide an example of how DA system could exacerbate the problem?
Sure, yes. There are several examples. I think the easiest one to understand is that the DA system, through the background air covariances, tends to make multivariate adjustments, right? So if you change temperature somewhere in the mid latitudes, you also have to modify the wind field, otherwise you get an unbalanced increment. And so if you have biased observations in one variable, the multivariate nature of data simulation can introduce biases in other variables. And there are lots of examples of that, maybe not so much with wind and temperature, but for example, with some of the satellite observations and channels that are sensitive to both humidity and temperature, for example, they may make large temperature, humidity adjustments just because the temperatures are mismatched. And that's not, in some cases, that is systematically the wrong thing to do, depending on the situation and the other constraints. So that's the basic mechanism through which biases in one variable can easily creep into the others.
Go ahead, yeah.
Joshua Wu, can you unmute yourself? I cannot unmute you if you want to ask a question. Joshua Wu?
Yeah?
You can unmute yourself, just ask your question. You raise your hands, right? There's no more question in the question box. Anybody want to ask a question? You can just speak out. We can unmute you. So, yeah, looks like we don't have any more questions.
Okay. Well, if people have questions later that they come up with, they can always contact me.
Yes, please, if you want to, you can contact Dr. D directly. If you need assistance, just write to us. We are going to make the recording and the PPT slides available on the UFS portal. Thank you, everybody, for participating. Thank you, Dr. D, for the wonderful talk.
My pleasure.